Hello everyone, I welcome you all to the new video. This video is going to be about the problems in chemistry section for GATE Excel. So let us begin with some of the problems. I will discuss 10 problems which are very important from the exam point of view. I will show you how you can solve these problems with the right approach and with the right formula and how to arrive at the correct answer. So without any ado, let us begin with the video. Let's take a look at the first question. 1 gram of protein is dissolved in 1 liter of water. The resulting solution exerts an osmotic pressure of 1.4 torr at 298 Kelvin. Assuming that the protein does not ionize in the solution, the molecular weight of protein is dash grams per mole. So in order to solve this question, you should know what osmotic pressure is. Osmotic pressure is the minimum pressure that you must apply to a solution in order to halt the movement of solvent molecules from a lower concentration to a higher concentration. So here I is the Van 't Hoff factor, which is equal to 1, because your protein doesn't ionize once it gets into the solution. So osmotic pressure, which is denoted by pi, is equal to I into m into r into t. So I over here is 1, which is a constant, and m is the molarity. Molarity and r is the universal gas constant, and T is the temperature, which is given in kelvins. Make sure that you convert 1.4 torr into atmospheric pressure, because the unit of R here given is 0.082 liter atmospheric pressure per mole per Kelvin. The relation between torr and pascals, which is Newton per meter square, is 760 torr is equal to 1,01,325 pascals or Newton per meter square, which is equal to 1 atmospheric pressure. So 760 torr is equal to 1 atmospheric pressure. Therefore 1.4 torr is equal to 1.4 divided by 760 atmospheric pressure. So we have converted our 1.4 torr pressure into atmospheric pressure. Let us put the value. So pi, which is equal to I into molarity, gram of the solute divided by its molecular weight into the volume in liters into R into T. So shift your molecular weight to the left side, because this is the value that we are going to find, and put the values. You will get 13,265.2571 daltons. The molecular weight of the protein is in daltons. So this is your final answer. On to the next question. Here we have given activation energy of the two reactions. The difference of the activation energy of the two reactions, which is 5 kilojoules per mole. And pre-exponential factors for these two reactions is also given, and it is mentioned that they are of the same magnitude. Then we have to find out the ratio of the rate constants for these two reactions. Now the formula for the rate constant for any reaction is given by K, which is the rate constant, is equal to A, that is the pre-exponential factor, into E raised to minus of EA upon RT. Your EA is the activation energy. So let us put the values for individual reactions. So before we put on the individual values, let us take the log of natural logarithm of both the sides, so that it eases the calculation. ln of K1 is equal to ln of A1 minus of EA1 upon RT, because natural logarithm of E is 1. And similarly for the next reaction is ln of K2 is equal to ln of A2 minus E. So we can both subtract the equation, subtracting the second equation from the first equation. You will get ln of K1 minus ln of K2 is equal to ln of A1 minus ln of A2 minus EA1, that is activation energy for the first reaction, upon RT, plus activation energy of the second reaction upon RT. Here you have to keep in mind that the pre-exponential factors for both the reactions are same, and also these both reactions are carried out at the same temperature. So you can write ln of k1 minus ln of k2 as a ratio, that is ln of k1 upon k2 is equal to 0, because ln of a1 minus ln of a2 are both the same quantities. So 0 minus ea1 plus ea2 upon rt. So at this point you can put the values of the individual quantities. Difference between the activation energy is given as 5 into 10 raised to 3. So we directly put the value of the both E1 plus E2 as 5 into 10 raised to minus 3 upon the universal gas constant, which is 8.314 into temperature, that is 25 degrees Celsius, that is 298. So after solving this equation and deleting the log, that is taking e raised to the whole value, that is 2.01804, you will get 7.52402. So this is the ratio of it will have no unit. Just make sure that whenever you raise any exponential function, especially e raised to something, just make sure that after decimal point you have 4 digits, because e raised to 2.0 might give you some answer like 8 point something, but in order to have your accurate answer, because a minute difference of point will have a great effect on your final answer. So make sure that whenever you raise something raised to e, make sure it has 4 digits after decimal point. 5. A protein in denatured state D is in equilibrium with the native state N. At 360 Kelvin, both N and D states are equally populated. If the standard entropy change for the reaction at this temperature, that is delta S0, is minus 139 joule per Kelvin per mole, then the corresponding standard enthalpy change delta H0 for the reaction in kilojoules per mole is. So here the protein is in denatured state and it is in equilibrium with the native state. At 360 Kelvin, you have both denatured and the native state of the protein whose concentration is not changing because it is in equilibrium. The forward and the backward reaction rates are same. Therefore, N and D states are equally populated. So here you have to calculate the delta H for the reaction, for this reaction, equilibrium reaction. So you have your entropy, you have the temperature, and you have, it's been mentioned that the reaction is in equilibrium. So the one equation which relates these four quantities is delta G is equal to delta H minus T delta S. Here T is the temperature, delta S is the entropy, delta H is the enthalpy, and delta G is the standard free energy change. As the system is in equilibrium, your delta G0 will be 0. Therefore, put the value of 0 and the temperature entropy in the equation, and after solving you will get minus 50,040, and convert it to kilojoules, you will get minus 50 kilojoules per mole. Question 6. The pH of 1 liter buffer solution containing 0.2 mole of acetic acid and 0.3 mole of sodium acetate is 5. The K, that is dissociation constant of acetic acid, is P into 10 raised to minus 5, where the numerical value of P is. So this is a straightforward equation. There's a little twist. You have to find out the value of P. And you have been given dissociation constant in the form of P, that is P into 10 raised to minus 5. So the pH of the solution is given, that is 5. The pKa, you have to find out the pKa. pKa is just the minus log of Ka, the dissociation constant, to the base 10. So put the values in the Henderson-Hasselbalch equation for the acid. Your acid is acetic acid, which is 0.2 molar because there are 0.2 moles of the acid in 1 liter. So you will get 0.2 molar. And your conjugate base is sodium acetate or just acetate, which is 0.3 molar. That is 0.3 moles per 1 liter. So put the values. Your pH is 5. And your pKa is minus of log Ka to the base 10, and the ratio of Ha upon H minus, that is acid upon conjugate base, that is 0.2 upon 0.3. So after solving this equation, you will get P is equal to 1.5. So this is a super easy question. You just have to keep in mind the Henderson-Hasselbalch equation is useful in order to calculate the pH range of the buffer. So here we are just calculating the dissociation constant value, which is given in the form of P, that is P into 10 raised to minus 5. So Henderson-Hasselbalch equation is the most important formula over here, without which you cannot solve. This question is going to be super easy. Here you have been given two equations, two reactions, that is 2 moles of X is in equilibrium with Y, and the product of the first reaction, that is Y, is the reactant for the second reaction, that is Y will directly give you P, which is product. So here you have to find out the rate of change of product P with respect to time. Now from the rate equation, it is clear that rate of change of P with respect to time is equal to K into the reactant Y. But if you look carefully, you have K equilibrium for the first reaction. K equilibrium for the first reaction is K equilibrium is equal to the rate of forward reaction upon the rate constant for the backward reaction. But the velocity of the forward reaction is given by Kf into x square, while the velocity, that is the rate of the backward reaction, is given by Kb into y, which is understandable as we did for the second reaction. Now, if you shift the values, and you will get y, which is equal to kf, that is the rate constant for the forward reaction, into x square upon the rate constant for the backward reaction. Now put the value of y into the above equation. You will get k into kf by kb into x square, but kf by kb is equal to k equilibrium. So you will get dp by dt, that is the rate of change of product with respect to time, is equal to k, that is a rate constant for the second reaction, into k equilibrium for the first reaction, into x square. Let's move on to the next question. So here you have been given two reactions of carbon. One carbon is in the form of graphite, while the second carbon is in the form of diamond. And both these forms of carbon react with oxygen to give you, of course, carbon dioxide, because both of them are chemically similar. So they're similar. So their standard enthalpy change has been given, that is minus 393.5 kilojoule per mole for graphite changing into carbon dioxide, while minus 395.4 kilojoule per mole for diamond changing into carbon dioxide. So this whole question is based on Hess law, which states that the change in enthalpy in a chemical reaction, that is the heat of the reaction at constant pressure, is independent of the pathway between the initial and the final state, which in short summarizes to no matter what pathway you choose for completion of your reaction, the overall change in the enthalpy is always going to be the same. So you have to find out delta H0 for conversion of graphite into diamond. So if I represent graphite as A and oxygen as B and carbon dioxide as C, you will get the equation A plus B is equal to C. Similarly, for diamond, D plus oxygen B will give you C. Now suppose if I reverse this reaction, your delta H0 for the reaction changes and it becomes positive. You have delta H2, that is delta H2, you have minus 395.4, but when I reverse the reaction for diamond, you will get delta H2 is equal to plus 395.4. Now I add these two reactions, which will give me so if you look carefully, the product of the first reaction is the reactant for the second reaction. So CC will get cancelled and you will get A plus B is equal to D plus B. If we add the enthalpies for each individual reactions also, if you add them, you will get 1.9 kilojoule per mole. And BB, that is oxygen from both the sides, will get cancelled. So you will get A is equal to D. And this is exactly what we want, graphite changing into diamond. So the answer, that is the delta standard enthalpy change for graphite changing into diamond, is 1.9 kilojoules per mole. Go on further and discuss the next question. So here you have been given standard reduction potential of two metals, copper and silver. The standard reduction potential for silver is 0.8, while the standard reduction potential for copper is 0.34. So when you have two values for two different metals, the value with the higher number is more likely to get reduced. So here in this case, silver is more likely to get reduced, while copper is more likely to get oxidized. And it is also visible from the equation. The oxidation state of copper changes from 0 to +2. Therefore, the oxidation state is increased. Therefore, copper is oxidized over here. While in case of silver, you have oxidation state of +1, which goes on and reduces to 0, which means silver is reduced. Because silver has more oxidation, standard reduction potential, that is 0.8. Therefore, it is more likely to get reduced. So you have to find here standard free energy change. So one equation which relates these two quantities is delta G0 is equal to minus of N into F into delta E. And delta E is the difference between the standard reduction potential for the one element which is being reduced minus the standard standard reduction potential for the element which is oxidized. So silver is reduced over here while copper is oxidized, therefore 0.8 minus 0.34 into 96,500, which is a Faraday's constant, and it has unit coulomb per mole, into 2 because 2 electrons are being transferred from one species to another. So when you multiply this whole three numbers, you get delta G0, which is standard free energy change, is equal to minus of 88.780 kilojoules per mole. Thank you for watching the video till the end, and if you think you need a little more longer videos, please do not hesitate to mention it in the comments below. I will be happy to come up with the next one.